Students, in the last class, we had studied about the concept of resistivity, resistance, conductivity, conductance, and so on. Even we had derived expressions connecting them. Today, we have to learn about a device or what you call as a element, circuit element known as resistor. So, resistor, what is a resistor? A resistor is a material of known resistance. Many a times it is also said to be a device which is used to control the flow of current in a circuit. So, a resistor is a material of known resistance or a device which is used to control the flow of current in a circuit. See, this is the circuit symbol of a resistor. There is no hard and fast rule as to how many peaks and downs should be there. But this is the way how you write the circuit symbol of a resistor in any circuit. This is how you represent resistor in any circuit. So, next to understanding resistor, we have to know about the EMF of a cell. What is EMF? EMF represents electromotive force. Electromotive force is called as EMF. So, EMF of a cell, see, when you connect a cell, basically what is a cell? Cell is a source of EMF. It is a source of EMF, and when you connect a cell in a circuit, the main intention of connecting a cell in a circuit is to drive current in the circuit. So, here you have a cell connected in the circuit. Remember, whenever you think of a cell, whenever you think of representing a cell, it has been represented by two parallel lines like this. The longer line always represents the positive terminal of the cell, and the shorter line represents the negative terminal of the cell. So, to understand what is EMF of a cell, EMF of a cell is the work done to drive unit charge once completely round the circuit. So, as the name itself tells you, look here, electromotive force. So, this cell always motivates charges to flow through a circuit. Why does the charges flow through a circuit? Charges basically move through a circuit or move from one point to another point whenever there exists a potential difference. So, because of the potential difference, charges move from one point to another point. Here also, when you include a cell in a circuit and switch it on, a potential difference will be created between 2 points in the circuit. So, the charges will be motivated to move from region of higher potential to region of lower potential. So, that is the intention of connecting a cell. So, EMF of a cell, electromotive force of a cell, is the work done to drive unit charge once completely around the circuit. So, here you have a cell connected in a circuit. This is what is called as external resistor in the circuit, represented as R. Normally, external resistor has been represented by capital R. Now, when you have connected the cell motivates the charges to move through the circuit. That means the cell does some work in moving the charge through the circuit. The work done by the cell to move a unit charge once throughout the circuit. Throughout the circuit means, for example, if you think of a charge starting from positive terminal, then the work done in moving the charge back to the positive terminal after going through the circuit completely once, that represents the EMF of the cell. That work done represents the EMF of the cell. So, see here, why work has to be done? There is some opposition for the movement of charge. That opposition is what is called as resistance. In fact, here you will understand that the resistance offered here is in two stages. One, by the external resistor, what we have represented as R, and also there will be a resistance offered by the electrolyte of a cell. A cell always consists of two electrodes, one positive electrode and negative electrode, and between these two electrodes there will be electrolyte. That electrolyte also offers some resistance or opposition for the flow of charges. That opposition offered is what is called as internal resistance. So the cell has to do work in moving the charge against two resistances, one the external resistance and also through the internal resistance. This total work done in moving a unit charge once throughout the circuit is what is called as EMF of a cell. Remember, EMF of a cell is mathematically measured by the ratio of work done to the charge moved, W by Q. If you remember, this was also the same with respect to the potential. So the SI unit of EMF is also volt, represented by V. EMF of a cell is said to be 1 volt if 1 joule of work is done by the cell to drive 1 coulomb of charge completely round the circuit. So if you have 1 coulomb of charge and the cell does 1 joule of work in moving this 1 coulomb of charge once completely through the circuit, that is against the external resistance and also through the internal resistance offered by the electrolyte, then the EMF is said to be 1 volt, because mathematically W will be 1 joule, Q will be 1 coulomb. Joule per coulomb is what is called as volt. So the EMF of the cell is said to be 1 volt. So what is cell? Cell is a source of known EMF, or cell is a source of EMF. How do you represent it? It has been represented by two parallel lines. The bigger line always represents the positive terminal of the cell, and the shorter line represents the negative terminal of the cell. If you have many cells combined, then it is called as battery. Combination of cells is called as battery. ನಿಮ್ಗಳಿಗೆ ಮನೆಯಲ್ಲಿ ಹೇಳ್ತಾ ಇದ್ದಿದ್ದು ಜ್ಞಾಪಕಕ್ಕೆ ಇರ್ಬೋದು, ನಾವು ಟಾರ್ಚ್ ಅಂತ ಏನು ಯೂಸ್ ಮಾಡ್ತೀವಿ, ಎಷ್ಟೋ ಮನೆಗಳಲ್ಲಿ ಅದನ್ನು ಬ್ಯಾಟ್ರಿ ಅಂತ ಕರೆಯೋರು. ಯಾಕೆಂದರೆ ಅಲ್ಲಿ ನಾವು 2 ಅಥವಾ 3 ಸೆಲ್ಗಳನ್ನು ಯೂಸ್ ಮಾಡ್ತಾ ಇದ್ವಿ, ಅದನ್ನು ಕಂಬೈನ್ ಮಾಡ್ತಾ ಇದ್ವಿ, ಒಂದ್ರ ಹಿಂದೆ ಒಂದನ್ನು ಜೋಡಿಸ್ತಾ ಇದ್ವಿ. ಸೊ ಹಾಗಾಗಿ ಆ ಒಂದು ಕಾಂಬಿನೇಷನ್ ಆಫ್ ಸೆಲ್ಸನ್ನೇ ಬ್ಯಾಟ್ರಿ ಅಂತ ಕರಿತಾ ಇದ್ರು. ಸೊ ರಿಮೆಂಬರ್, cell is a source of EMF, battery is a combination of cells. What is EMF? Work done to move a unit charge once completely through the circuit. Remember, the EMF of a cell is always fixed. Okay, so when you say EMF, you are measuring the work done by the cell throughout the in driving a unit charge throughout the circuit, that is through the external resistance and also against the internal resistance. On the other hand, if you are measuring the work done by the cell in moving the charge only against the external resistance, only against these 2 points, then you call it as terminal potential difference. The work done in moving a unit charge against the external resistance of the circuit is what is called as terminal potential difference of the cell. In fact, that is also equal to the potential difference found across the terminals of the cell when current is flowing through the circuit. So remember, EMF, to measure EMF, you have to know the work done by the cell against external resistance as well as internal resistance. To measure the terminal potential difference, it is the work done against the external resistance in the circuit. Okay, next to this, we have to know what is a circuit. See, circuit is a combination of electrical sources and various circuit elements. It's a combination of various electrical sources. Electrical sources means like battery. You may have a battery, then you may have an alternating current source like what you call as oscillator, that will be connected with many circuit elements. Circuit elements means it may be a capacitor, resistor, inductor. All these are called as circuit elements. So the combination of all these circuit elements and electrical sources is in general called as circuit. So internal resistance of a cell, already I have told you, normally represented by small r. It is the work amount of opposition for the flow of current offered by the electrolyte of the cell. I told you. So in the previous case, so here the opposition offered by the electrolyte of the cell. Where will be the electrolyte? Between these two terminals. That opposition offered by this electrolyte for the flow of current or charges is what is called as internal resistance. Internal resistance is normally represented by small r. Then external resistance. External resistance normally represented by capital R. It is the amount of opposition to the flow of current outside the cell in a circuit. That's what we saw here. See, this is what is called as external resistance. This represents the amount of opposition for the flow of current outside the cell in the circuit. That's what is called as external resistance. So remember, for the flow of current in a circuit, two types of opposition would always be there. One is the opposition outside the cell, that is called as external resistance, and the other one is the opposition inside the cell, that is called as internal resistance. Next to this, we have to know what do you mean by cell in open circuit. See, a cell is said to be in open circuit condition if no current is drawn from it. That is, external resistance is, it's not zero, in fact it is infinity. External resistance, if it is infinity, then the cell is said to be in open circuit condition. So in such case, no current will be drawn from the circuit. As you can observe here. So here in an open circuit condition, the external resistance will be infinite. For example, see in this circuit, when you say external resistance is infinite, what you mean? You mean to say that this capital R is infinity. That means if this R is been removed from here, if you have a circuit like this, see if you have a circuit like this, what will happen? There is no external resistance connected here. There is no path for the charges to flow from here to here. Then we say that R is equal to infinity. Then the cell is set, then no current will be drawn from the cell because there is no path, completed path for the flow of current. Then we say that the circuit or cell is in open circuit condition. So if external resistance becomes infinite, the cell will be in what you call as open circuit condition. Terminal potential difference. Already I have told you about this. Potential difference across the terminals of the cell. See, if you are measuring the potential difference across the terminals of the cell, that is nothing but the work done in driving the current against the external resistance. So, in an open circuit, terminal potential difference is equal to the EMF of the cell. So, what happens is when no current is drawn from the cell, then EMF and terminal potential difference will be one and the same because no current is been flowing in the circuit. So the terminal potential difference will be same as the EMF of the cell. Whereas when current is drawn from the cell, terminal potential difference is less than EMF of the cell. See, these 2 points are very important. Potential difference across the terminals of the cell is what is called as terminal potential difference. But in an open circuit condition, that is when external resistance becomes infinity, the terminal potential difference will be equal to the EMF of the cell. In fact, mathematically also we will be proving this. But when the circuit is closed, when the current is flowing through the circuit, the terminal potential difference will be less than EMF of the cell. Remember, only when the circuit is in open circuit condition, EMF of the cell will be equal to terminal potential difference. In all other conditions, you will find that the terminal potential difference will be less than EMF. This is when closed circuit. That means current is being drawn from the circuit. Whereas this is open circuit. See, these points are very important, particularly for 1 marks and for your entrance exams. So E is equal to V when external resistance is equal to infinity. This also you have to remember. When external resistance is equal to infinity, EMF will be equal to terminal potential difference. That is what is called as open circuit condition. In closed circuit condition, that is when capital R, that is external resistance, is finite, terminal potential difference will be equal less than EMF, because the work done here in case of EMF involves both external resistance and internal resistance, whereas terminal potential difference involves only the work done against the external resistance. Hence, terminal potential difference will be less than EMF of the cell. Next is, we will derive an expression for current drawn from an external resistor and terminal potential difference. So here we have a resistor connected in the circuit. The EMF of the cell here connected is E and internal resistance is R. I is the current flowing through the circuit. Students, remember, whenever we write a circuit, we always indicate what is called as conventional current. Conventional current is the current flowing from positive terminal to negative terminal. So this is the current flowing through the circuit. V is the potential difference found across the external resistance. In fact, this is what is called as the terminal potential difference, and V dash is the potential difference across the internal resistance. So V is the potential difference across the external resistance, V dash is the potential difference across the internal resistance. So when current flows through the circuit, work is being done by the cell both against capital R and small r. So V is the work done against capital R, V dash is the work done against small r. So EMF of the cell is the sum of both V and V dash, V plus V dash. From Ohm's law, you know that V is equal to I into R and V dash will be equal to I into small r. So substituting in this equation, E is I into R plus I into small r. The same current flows through both. So I can be taken out as common. E is equal to I into R plus R. Or I is E by R plus R. This is the expression for current flowing through the circuit in terms of EMF of the cell connected, external resistance in the circuit and internal resistance of the cell. But from Ohm's law, we also know that V is IR. V is what is called as terminal potential difference. So we have the expression for I, E by R plus R into capital R. So terminal potential difference is also given by ER by R plus R. This is the expression for terminal potential difference. See the difference. I is E by R plus R, V is ER by R plus R. So again, if you consider V by I ratio, you will get back R. That's according to Ohm's law. When R is infinity, when external resistance is infinity, I had told you a few moments ago that when external resistance is equal to infinity, terminal potential difference will be equal to EMF of the cell. So if you substitute R as infinity here, you will observe that V reduces to E. See, I can prove here. See, V is ER by R plus R. What I will do is ER by, I will take out R as common here. So it is 1 by R plus R. So if capital R becomes infinity, what happens? If capital R becomes infinity, this term becomes 0, then V would be equal to ER by R, which is equal to E. So remember, V will be equal to E when R is equal to infinity. This is the expression current for the current drawn from the external resistor. Okay, students, thank you. I will stop at this stage. We will continue in the next session.